On this video, I thought I'd try to derive the character table for S4. And so, of course, you have to know the conjugacy classes. And as we've seen in this course, permutations are conjugate based on their cycle type. And so what are the possible cycle types for a permutation on 4 elements? Well, either a 4 1 cycles, a 2 cycle and 2 1 cycles, 2 2 cycles, a 3 cycle and a 1 cycle, or a 4 cycle. And in case we need to know this information, there's 1 permutation of that type, 6 permutations of that type, because there's 6 ways to pick the elements in the 2 cycle, 3 elements of this type, because you have to pick 1 element to go with A1 in 1 of 3 ways, and then the remaining 2 elements have to go in the other 2 cycle. There are 8 3 cycles in S4, because you just pick 1 of 4 elements to not put in the 3 cycle, and then there's 2 possible ways to orient the 3 cycle. Finally, there are 6 4 cycles. Namely, there are 4 ways to specify the order on A, B, C, D. So that's 4 factorial options, but then up to cyclic shift, you get the same cycle. So dividing by 4, you get 6. So it's worth noting for the purposes of proofs, one way to get representations is to go with permutation representations. This is one approach. I mean, one thing I could have used that I didn't in this case was that actually S4 acts on S4 modulo its commutator subgroup, which is A4, which gives you Z mod 2Z. It is one of the homework problems that the one-dimensional representations of G are actually in one-to-one correspondence with the representations from G mod the commutator. So you could start with that in order to start to get representations. But I'm going to be a little bit more clever and try to get work out of stuff we've already done. If you actually act on S4 mod V4, that's isomorphic to S3. So there's this quotient map from S4 to S3. And in particular, for any representation we already have for S3, you can compose it with this homomorphism, and you now have a representation for S4. And what's particularly nice about this particular example is that the 6 permutations of S3 can actually be chosen to be coset representatives for this coset space. So this isomorphism is literally just equality in some sense. And so the point is, we can use the table we've already derived for S3 to get representations, or to get characters for S4. So here's our facts. Now, one thing we need to figure out what to do is to figure out the character values. So we get, from our 3 irreducible representations of S3, we now get 3 representations of S4. Note, they might not be irreducible. That has to be checked, and sometimes this technique doesn't work. So let's see what happens. The trivial representation is still trivial, so the character values are all still 1. We can see what happens with phi of 2. Well, it's the sign representation, but a 2 cycle under this homomorphism gets sent to 1, 2, V4. So we only need to figure out what it does to 1 map. So 1, 2 gets sent to 1, 2, V4. Under the representation phi of 2, that's -1. So -1 is the character value there. Similarly, a product of disjoint 2 cycles actually belongs to V4. So under this homomorphism, 1, 2, 3, 4 gets sent to the identity element in S3. So under every character value, that's going to get sent to whatever the representation or whatever the character is at the identity. So in other words, this column is going to match this column exactly. So that means we should copy the 1 here and the 2 as well for the third irreducible representation. Now what happens to 3? Well, 1, 2, 3 gets sent to 1, 2, 3, V4. So it gets sent to itself in the symmetric group. So again, you just get the character value copied from the previous character table. So these 3 columns are copied from the previous character table, and this one's just a duplicate of the identity column. So then you just got to figure out what happens to a 4 cycle. Well, it turns out the 4 cycle is equal to this coset with 1, 3. You can check that by showing this calculation. And so then you're just looking, if you want to compute the character of this element, it's the character of this element. And that's a 2 cycle in S3, and so then you're just copying this column. So each of these corresponds to a column from the character table from S3. And those are all the representations we can get from S3. So a fact I forgot to say in an earlier video is when you have a representation and you take the inner product of its character with itself, you only get 1 when it's an irreducible character. So that's a pretty handy result. So it's possible that these were no longer irreducible, so we still need to do this calculation and see that they remain irreducible. So let's do the calculation with phi1 with itself. 1 plus there's, what is this? 6 permutations of that type, 3 permutations of type 2, 2, the 8 permutations of type 3, 1, and the 1 permutation, the 6 4 cycles. That adds up to 24, but remember we're supposed to be dividing by the order of the group, so congratulations, the trivial representation is still irreducible. Okay, that's always true, but it's worth checking anyways. To see this one is true, just notice that the only difference between these 2 rows is a bunch of minus signs, and when you square a minus sign, it becomes positive. So up to squaring the entries, it's the same calculation. So the only one that's interesting is the third one. The first entry becomes 4. The third entry is 3 times 4, because that's 2 squared, and the third entry is 8 times 1. Congratulations, that still adds up to 24. So when you divide by 24 like you're supposed to, you get 1. So sometimes applying homomorphisms, surjective homomorphisms from one group to another allows you to use the character table from another group to get irreducible characters from your larger group. Note there are 5 conjugacy classes, so there's still 2 irreducible characters missing. What do we know about this? We know that the sums of the dimensions squared has to add up to the order of the group. So we see whatever these remaining 2 irreducible representations are, the squares of the dimensions has to add to 18. It's clear then that they both have to be 3-dimensional, because, well, the only options left have to involve integers 1 through 4, and you can check that the only combination that works is both being 3. So we're looking for two irreducible three-dimensional representations. Unfortunately, that doesn't help us much, because if we were down to one, we could use linear algebra, but we need to find two more. Well, one trick is to use other representations. So we already know a good representation from S4 to itself, the identity map. And so this gives rise to a homomorphism to GL4R by just viewing permutations as permutation matrices. Quite literally, given the standard basis, a permutation acts on a basis vector by permuting the basis vectors. So that's a four-dimensional representation, and our hope is maybe we're going to get lucky and there's a three-dimensional representation inside it. Because I already mentioned, permutation representations always contain the trivial representation as a submodule. So we know that you're going to be able to knock off one dimension anyways. So the hope is that the remaining three-dimensional representation is irreducible. So let's try that, because we don't have any other options. So remember, the sum of the four basis vectors, any permutation is going to be the same vector. So the span, this vector is S4 invariant, and so the span is as well. It's a one-dimensional subspace. Its complementary subspace are those vectors whose four coordinates all add to 0. You can see that the span of this vector space and this vector space only intersect in the origin. This vector space is therefore three-dimensional, and Sn acts on it by permuting coordinates. So there we have a three-dimensional representation. Let's see if it works. Let's take this as our basis. Just differences of pairwise basis vectors. So the sum of the coordinates is in fact 0, because it's 1 minus 1, plus a bunch of zeros. Now let's take one permutation from each conjugacy class, let it act on the basis vectors, and see what the matrices are. So 1, 2 on F1 sends becomes what? E2 minus E1, so that's just its negative. So with respect to the basis, that's the column vector for this matrix. Similarly, if I act on F2, I get E1 minus E3. You can see that E1 minus E3 is F1 plus F2. So in terms of basis vectors, I get this column. Finally, 1, 2 is not involved in the last vector, so it fixes it pointwise, so the last column is that. This matrix has trace 1. So for that character in that conjugacy class, we expect trace 1, or the value to be 1. Similarly, with these other matrices, 1, 2, and 3, 4 permutes, negates the first and last basis vector. And what does it do with the middle vector? It sends it to E1 minus E4, which is clearly the combination of F1 plus F2 plus F3. So it's this column vector. Similarly, if I act by 1, 2, 3, let's see. E1 goes to E2, E2 goes to E3, so F1 becomes F2. So I get this column vector. On the other hand, E2 becomes E3, E3 becomes E1. So one, two, three dot F2 becomes E3 minus E1. Notice that's the negation of F1 minus F2, so that's that column vector. And finally, when you act on F3, you get E1 minus E4, which is a typo here. That should be the summation of all three. Finally, if you act with the for cycle, you get this matrix. And so one element from each conjugacy class. I calculated the actual matrix for the sake of being able to write down the traces. Because remember, the trace is constant on conjugacy classes. So now I know the character value. The character value is 1 on this conjugacy class, 0 on this one, -1 on this one, and -1 on this one. So the character for this three-dimensional representation is this. Now you can check, as I have here, that if you compute, you actually do get orthogonality, like you're supposed to. Of course, I could have got simpler and just check what happens when I multiply it by itself. That the response is 6, 12, 18, 24. So its inner product with itself is in fact 1. And so it is in fact irreducible. Note, of course, this doesn't imply that arbitrary class functions being orthogonal makes them irreducible characters. The statement is that if your class function is a character and it has this feature, then it comes from an irreducible representation. So now we're down to one more. Now we can do the linear algebra method. And of course, if by doing the sanity check, you can see the difference here is +6 and -6. This comes from having a 1 here and a -1 here. I could see that if I just change those 1s and negate them, the same calculations work. And so you end up with some other vector that's orthogonal to the first 3 rows. Of course, that doesn't mean it's a character. But we can check that it is orthogonal to the last character we had. 9 minus 6 plus 3 minus 6 is 0. So we have 5 orthogonal class functions. 4 of them correspond to irreducible characters. We know that the irreducible characters form an orthonormal basis. Therefore, this also has to correspond to an irreducible character. Therefore, we have the character table for S4. And so the main techniques we saw is using representations from smaller groups and permutation representations. And that usually those are how you handle this situation where you end up with 2 unknown rows. You have to go searching for other representations.